This is our final presentation on our CubeSat. We're Team the Thinker, and our slogan is Those Who Think. My name is Christopher Beck, and I'm working alongside Andrew Duvall, Devin Cosgrove, Ryan Eder, and Warren Tan to complete this challenge. The Thinker is a team of Leland High School students known for our analytical skills and passion for engineering. We're based in Almaden Valley, San Jose, and we embrace innovation and problem solving. Our work reflects our commitment to logical reasoning and teamwork as we strive for success in the CubeSat competition. Our team's goal is to develop a reliable system for detecting power outages on Earth utilizing image detection systems on our CubeSat. Our CubeSat relies on several key systems to function effectively. The computing and control system uses a Raspberry Pi as the main onboard computer to process data, while a ground control laptop receives and analyzes the information. For communication, a USB adapter facilitates data transfer between components, and finally, the imaging subsystem features a Pi Camera Module 3, which captures images for us to detect power outages from space.
The CubeSat structure consists of metal brackets and polycarbonate panels. The metal brackets, which are crucial for assembling the CubeSat, give it structural integrity and stability, while the polycarbonate panels form the overall CubeSat structure and secure the electronics in place. The altitude control and determination system on our CubeSat is the IMU, which ensures proper orientation and position using various instruments. With an accelerometer to measure linear acceleration, a gyroscope to measure angular velocity, and a magnetometer to detect Earth's magnetic field, the IMU is able to detect its position and rotation relative to a starting point, which is useful in navigation properly angling the camera towards Earth. This is our CAD model of the CubeSat, made using Fusion 360.
Here's a brief look at our power budget and system overview. So the solar panel will generate the power for our CubeSat while the power bank will store and regulate the power supply. For our power systems, it's important to understand that our solar panels will not perform at peak efficiency due to the many external factors and lighting conditions, some of which include angular positioning and shadowing. Approximating that the panels would work at 80% efficiency, the CubeSat would require around 16 panels in idle and 18 panels when running. To be sure that there is constant power available, around 20 solar panels would be an optimal number to power the CubeSat. Additionally, to limit power consumption, the CubeSat can charge the battery in a specific off state and turn on temporarily to run the program to take photos.
Our CubeSat will orbit 400 kilometers above the Earth's surface, which is about the same altitude as the ISS. The lower orbit allows for better image resolution. The inclination of our orbit will be about 97 degrees, which enables a sun-synchronous orbit. This will provide consistent lighting for our image-taking purposes, and the solar panel generation will be optimal. The period of our orbit will be 90 minutes, and it will pass over the same locations each orbit. However, this orbit does have some limitations. There will be higher power consumption due to transmission over longer distances when compared to lower Earth orbits, and the hostile environment of space may impact the Raspberry Pi's performance.
For our CubeSat's imaging system, we need to calculate the ground sample distance (GSD) and the field of view to understand the resolution and coverage of our camera in orbit. First, let's look at GSD, which tells us the real-world distance represented by a single pixel in our image. From a 90-degree angle, the camera would display around 118.1 meters per pixel. With this given value, we can approximate the field of view, or the pixels in each direction of the camera. Using our GSD value, we can conclude that the camera at a 90-degree angle can display a photo around 544 kilometers wide and 306 kilometers in length. However, it's important to note that these values may vary based on the angular position of the CubeSat.
This is our original image capture algorithm. Due to time constraints, I cannot go in depth into this, but later on in our presentation, it is explained why we switched to a different image capture algorithm. Our final image capture algorithm used time instead. It would start, capture the first image, wait 5 seconds, and then capture the second image. The reason why we used time instead is because this allowed us to keep the CubeSat still and then change the lighting status of the environment. This allowed us to ensure the two images were of the same spot, and therefore our comparison could be far more accurate. Now, our image detection algorithm. Due to the previous image capture algorithm, the image detection algorithm receives two images to be compared, a first image and a second image. The image detection algorithm then converts both images to grayscale and splits it into 10 by 10 pixel squares. It calculates the average brightness of each 10 by 10 pixel block and takes the difference between the initial and final average brightnesses. Then it compares that difference to a threshold value. If the difference is greater than a certain threshold, then it's considered a possible outage. If it's less than the threshold, then it's marked as outage unlikely. And if it's less than the negative version of that threshold, then it's marked as power restored. After this is done, the output is added to a 2D array as either outage, restored, or same for each block. Now here's the algorithm for conversion of this data to an outage map. First, the algorithm starts and enters a nested loop that goes through each 10 by 10 pixel block in the 2D array. Then, the algorithm checks if each block is outage, restored, or same within this loop. Then, if it's marked as outage, it creates a red square using draw dot rectangle over the block. If it's marked as the same, it does nothing. And if it's marked as power restored, it creates green square using draw dot rectangle over the block. After all this is done with each 10 by 10 pixel block, we save the modified image as a PNG. Then, all images are exported to GitHub, and the 2D array is saved as a CSV, which is also exported. Then, this algorithm ends.
To properly test our CubeSat systems and program, we needed to design an effective testing environment. To ensure our design would function how we wanted, we created a list of criteria and constraints to guide the process. We needed a setup that allowed the CubeSat to be consistently moved in a controlled and constrained way. We also needed the CubeSat camera to be able to observe a lighting apparatus to simulate power outage, all while avoiding making permanent modifications to the CubeSat. For our constraints, we decided that our solution had to be a quick project to allow us to start testing sooner and under $50. We also agreed that hardware used in our solution must be easily sourced from local stores. It also needed to be small enough to easily be transported between team members' houses by car and have a way to quickly release and attach the CubeSat to the testing rig. The testing rig we decided to make was a self-designed one-axis linear gantry. This two-rail design effectively constrains the CubeSat's movement to one axis, allowing us to precisely control and monitor the CubeSat's movement using the IMU. The carriage that carries the CubeSat only contacts the guide rail through 12 ball bearings, making the movement of the satellite extremely smooth, removing potential bumps and vibrations that may result from overcoming static friction, ultimately reducing potential errors in our testing scenario. By attaching the carriage to the rail using dovetails secured by friction-fit pins, removal from the rail is quick, simple, and toolless. Additionally, the CubeSat attaches to the carrier plate through two 3/4 inch 4-40 button head screws through pre-existing holes in the CubeSat frame. And the plate is also quickly released from the carriage through friction-fit pins, allowing for quicker and simpler code modifications. While our CAD displays a structure made up of 2x4 wood planks, we decided to leave these out of the final assembly to make the gantry smaller and easier to transport. Additionally, the lighting setup to simulate power outages is not shown in the CAD for simplicity. This is our bill of materials for the linear gantry. Since a majority of the parts were 3D printed, the setup only costed $43.56 to make, which is under our $50 budget defined in our constraints, with a majority of the cost being the wooden dowels and Christmas lights we used. A short description of each part is provided in the rightmost column, and all purchased parts were sourced at local hardware stores such as Home Depot. The 3D printed parts were printed out of PETG on my 3D printer at home at a cost of $20 a kilogram. The testing setup, shown to the right, was propped the two linear rails on two chairs over a set of Christmas lights, which simulates light coming from the communities down on Earth when the satellite orbits. The smooth, linear movements approximate a short tangential segment of the real orbit over a small distance. In addition, the code captures images of lights based on an internal timer, which are then fed into the image detection algorithm. While this testing setup gave us a consistent and controlled environment to test the CubeSat code and systems, this does not fully reflect the unpredictable nature of a space mission. Some drawbacks of the setup include the lack of any angular change involved in orbit. Additionally, the distance between the lights and the CubeSat is much closer and does not properly reflect the CubeSat perception of data from space. The setup also does not account for any potential view obstructions the satellite may encounter in space, such as clouds. Finally, the tests were conducted indoors, and so the solar panels could not properly be tested at the same time as the image capture program, However, we did test the solar panel separately.
Now let's look at our mission demonstration. First, we see a test where the lights start on and they stay on. The code is ran through SSH and the results are uploaded to GitHub. As you can see, there is a brightness overlay. Here we see that there were no false positives or negatives. Now here we have a test that shows on and then off, which allows us to determine whether our program can effectively detect a power outage. Here we see that it did succeed in detecting power outages, although it did accidentally detect power restored in the top left corner. This could be caused by some sort of change in global lighting conditions. Now here we have a test where the power was initially off and then the power became on. And as you can see, here's an image after analysis, and we see that the program largely succeeded in detecting power restored. Now lastly, we have an image where the power stayed off and started off, and we see that there are no false positives and no false negatives, meaning that the program succeeded.
Moving on to how we can scale it to our flight spacecraft, we need to change a lot of the materials we have to make it more durable and thermally resistant as it's in space. We should replace polycarbonate with anodized aluminum, have materials with low outgassing properties so that it won't damage any of our components, and have space-ready solar panels that can withstand the radiation or temperature in low Earth orbit. We also should replace electronic components with radiation-resistant ones that will last during longer-term missions that we have, and have onboard propulsion or redirection, as well as reaction wheels. Moreover, we should have communication and hardware that has things like long-range radio receivers and transmitters for communication between our ground station and the CubeSat. We should have vibration analysis of our parts so that it can endure a launch situation and not get damaged before it reaches outer space. And the software needs to be restructured so that it can incorporate a GPS or orbital duration to coordinate when it should take the images and make sure that it's taking it precisely in the same spot that it was before, and deal with the cloud coverage and if it's day or nighttime. All right, and now on to our sources of error. There are a couple of different issues that we encountered during this Build a CubeSat challenge, and the first one was the displacement that we tried to use to measure where the CubeSat was so that it could take a photo of the same areas was faulty, as it refreshed at 50 hertz, meaning that the acceleration of the CubeSat could change during that time, and that wouldn't give us the same true displacement that we wanted. And rather, we're going to work on time, as that better represents orbits and will give us a more accurate photo of the areas that we wanted. And in addition to that, our equipment did get damaged slightly as we stored it at the very start of this challenge, though we worked through that and got everything fixed. And the power outage detection system had a number of issues, as it would incorrectly measure the light as the light threshold was off, but we worked to fix that and worked through all the fine details so that it was perfect. And then for lessons learned, we learned a lot of things, and communication and flexibility is definitely one of the top ones that we learned, as it works to minimize the misunderstandings and increase our efficiency as a team. It would make us be able to sift through ideas and not be single-minded. We could actually change what we're thinking so that we can incorporate all of the good ideas that are out there. And then the importance of fail safes and your code is also a very, very helpful one, as it saved us a lot of time having just something that prints out that this section was completed without any problems, so that if anything is wrong in our code, we can go back and look through and notice the exact areas rather than having to look through all of our code for any errors. Then this will impact future missions, as we have worked on communication, which allows us to fix problems much, much quicker. It already is a baseline, as we did this once and we demonstrated that we are able to do this. And that begins other missions with Framework, as we can refer back to this CubeSat. And then we also definitely implement fail safes, as that saved us so much time for errors. And just knowing to have fail safes is very, very important for us. And then we also have more experience with one another, and we can understand what each other are thinking, as it won't be our first time working together, which makes such a difference in these projects. And then lastly, our schedules can align more, and we know how each other's schedules are due to working this time around. And lastly, our additional resources are in this QR code, that links to both all of our CAD models and our GitHub code. Thank you.